And I'll do one more for fun. All right, you can work together, it's fine. It's 1:40 right now on my watch, just turned 1:40. I'm going to give you till 2:05 to do these. That includes a 10-minute break. Okay, so you can take your break now if you want, or you can finish these, then take your break, but I will resume class at 2:05. All right. So this okay? Any questions? No? It's all good? Okay. I'm going to show you an application of this. A box is to be made from a cardboard sheet. Yeah, I did. Thank you for reminding. As shown below. Find a volume function for this box. Now I said I'm going to draw it below, but I don't have room, so I'm going to draw it over here. Find the volume function and then sketch it. All right, so we own a company and we're going to be constructing these boxes, and I guess we're using cardboard. Let's make it, instead of cardboard, let's do something more expensive. How about like aluminum? Aluminum, all right, that way it makes a little more sense. Cardboard's pretty cheap. So I'm constructing this box, and here's what happens. I go to the people who supply me with the aluminum, and they give me a 12-inch by 24-inch sheet of aluminum. All right, understand? Flat aluminum sheet. Let's see if I have a sacrificial page. Yes, I brought it. Okay, so what we're going to do is we're going to cut corners out of this sheet of aluminum. So I'm going to come in here, put a little dotted square in here, a little dotted square here, a little dotted square here, dotted square here. So all those squares are the same, and I'm going to cut that, cut it out, right? Does someone have another sheet of paper I can sacrifice? There we go, perfect. So here it is. I'm just going to do some small little corners out right here. This. Those are about the same. All right, and I'm going to take this and I'm going to fold up the sides like this. Okay, then I'm going to come through and I'm just going to weld up the sides. All right, so these are permanently affixed. And now I could put something in this box, right? Yeah. And so this box has a volume to it. Do y'all remember what the formula for the volume of a box is? Length times width times height. Okay, so if I take how long this side is times how long this side is times how deep it is, that'll give me the volume. Right? Okay, so this has a certain volume. That's my idea, my plan to do that. Then someone else comes along and says, you know what? We want to get the most volume we can in this box. So I'm going to cut a bigger square out of each corner. What's going to happen when I cut bigger squares? The height is going to increase, won't it? So if the height increases, are we going to get more volume? What's going to happen? I mean, I agree that the height's going to increase.
The length and width will
the length and width are going to decrease, right? So let me just finish this off here. So I have two boxes now, right? So which one of these holds more, or do you think that they're the same?
Same.
Think they're the same? Let's do a vote. How many of you think that these are going to hold the same volume? Okay. Who thinks that they're going to be different? One. Okay. So let's check. Let's do it. Let's just do a quick sample. Let's say that this was 1 inch that we cut out. 1, 1, 1, 1, 1, 1, 1, 1, right? We cut that out. So when we fold up the sides and do this, we get that, right? How wide is it? Let's say that's this front edge right here. It was 12, but I cut an inch off here, and I cut an inch off here and fold it up. So now it's what? 10. Okay, this is 10 inches. And then this side right here, which would be that, right? Not the full thing, but that would be what? 22. And how tall is it? Well, it's the length of this, right? Which would be folded up. It'd be 1 inch. Okay. So what's the volume of this? 10 times 22 times 1, which would be 220 cubic inches. That's how much it would hold. Now, let's try a different scenario. Instead of doing 1, 1, 1, let's do 2, 2, 2, 2, 2, 2, 2, 2, right? I'll do that one in red. It's going to be a little taller, but not as wide. So, what do you got? Ember, I'm going to take 10 points off your next exam if you have that phone in your hand again. Got it? Okay. I'll give you a chance to redeem yourself, though. Show me that you can be in your phone and pay attention by telling me the dimensions of this box. Okay, we don't have time for that. So, what do we have? How wide is it?
8 inches.
What is this? 8? Because you took off, it was 12, right? You took off 2 here and 2 here. So that's going to be 8 wide. Then you took off 2 and 2, so it's going to be how long? 20. And how tall? 2. What's the volume of this? This is 160 times 2, 320. It's better. You were right. You were the only one who raised their hand, yes. Now, the next natural question would be, where should I cut it to get the most volume, right? Is there anything that tells you that this is the most? No. This was better than this, right? But that doesn't mean that this is the best. So as a business, from a business perspective, you want to be able to cut this in a way that you're getting the most volume out of the material, right? And it's not what most people think. Most people do think, so don't feel bad. Most people think it doesn't matter. You're going to get the same volume either way, but that's not the case. These are called optimization problems. We're trying to optimize the material here. So what we need to do before we can even answer that question of where do you cut it, which we're not answering, by the way, sorry, we're not going to be able to answer that. You have to do calculus to be able to do that. But to start, you have to come up with the function. You have to be able to generate the function. So that way we have some idea of how this behaves. As we let this vary, right? The cut is the thing that changes in each picture. That's our variable. How does that control the volume? So let's come back in here for our final try here, and let's not assign a value of 1 or 2 to it. Let's assign the value of x to the cut. and then I'll draw a picture with this very faded green marker, so hopefully it'll come up on camera. Ooh. Okay. How wide is that? The front side. 12 minus close? 2x. 12 minus 2x's, right? Whatever it is, 12, you take away 1 from each side, that means you're going to take away 2. If you take away 2 from each side, that means you're going to take away 4, right? So this is going to be 12 take away 2x. All right. How about this part? 24 minus 2x. Again, the 2x off each, or 1x off each side. And then finally, how tall is it? How high is it? X, right? Right there. So what is the volume? I'm going to switch to black again here. What is the volume of this hypothetical box that has a cut of x out of it? It will be, the volume is a function of x. So I'm using v of x instead of f of x. It'll be length times width times height, which will be the factor 12 minus 2x times the factor 24 minus 2x times the factor x. That's it right there. Now, my instructions to you were to get the function, right? Which we have. So we are pretty much done. We could talk about domain, although we haven't stressed it too much in this class. Is there some restriction on how big x can be? Like when I say cut out x, is there like a number that doesn't make sense to cut out? Like I could cut out 1 and 1, right? And 2 and 2, what wouldn't work?
The whole amount.
0, right, would be the smallest. If you don't cut anything out, you're not making a box, right? So I could say something like this. I definitely want x to be bigger than 0, right? But what would be another extreme?
Less than
24?
6.
6? Think about this. If this is 12 inches wide and you have to cut out x and x, 6 would be the most that would make sense. Because you'd be halfway, right? Halfway on the shortest side. Anything after that, it really doesn't make any sense. But even if you cut out 6 and 6, it's going to be 0 wide, and yeah, it doesn't matter. So this is a reasonable place to look, right? Now I'm saying this is not part of what you're going to need to do on the test. What I want you to be able to do is come up with the function. All right? Think you can do that? Okay. I want you to sketch it. So tell me right now, can you sketch that function the way it appears right now? What do you know right now for sure? Like, compare that, what you're looking at there, to what you did just now when I stepped out of the room. It's already factored, right? Isn't that great? But what don't we have? The end behavior, right? The end behavior, we don't have that part of it. So I can tell you right now that if I were to graph this, I could set each of those factors equal to 0. And by the way, am I going to cross or am I going to bounce at these? 1, 1, 1, cross at all of them, right? I'm going to cross at all of them. If I set them all equal to 0, 12 minus 2x equals 0, 24 minus 2x equals 0, and x equals 0, then you're going to get 6 and 12 and 0. Those are going to be your x-intercepts. So 0 here, 6 here, 12 here. But you don't know if it's up, up, down, down, right? You don't know that, so you can't really draw it yet. So how do we get to that point where we can get the degree and the leading coefficient? What are you going to have to do? Unfactor it, right? Unfactor it. And to unfactor it, that just means multiply it all together. So I'm going to start to multiply this together. I'm going to take these two first and multiply those. And then when I'm done, I'll multiply it by x. So when I multiply two binomials together, we have to do that FOIL thing, distribution, right? So what's 12 times 24? 288? 288. 12 times negative 2x, negative 24x. Negative 2x times 24, negative 48x. And finally, negative 2x, be careful here, times negative 2x is positive 4x squared, right? So plus 4x squared. This is our volume function. Yes. What am I missing still, though? The x on the far outside. So it's all of this times x. Y'all with me? Now there's one thing I can do. I could put these two together, couldn't I? What would that give me? Negative 72x. I'm going to keep that in mind, and now I'm going to pass an x through to each term. So v of x would be what? 288x, 72x squared, plus 4x cubed. And that's your volume function written out so that you can identify the degree and the leading coefficient. What is the degree?
3.
It's 3. It's the highest power of x that you see. This is n. What's the leading coefficient? The 4, right? That's your LC. And because of that, you have an odd degree, you have a positive leading coefficient, and you should be down up, right? Down up, and you're going to cross through at each one of these. So I'm going to go to the far left point, I know I need to go down. The far right point, I know I need to go up, and I'm crossing through all of them. So it's going to go like this, and like this, like this, and like this. Make sense? Now, if we step back and we think about the question, the word problem, I took a vote. I said, how many of you think that it'll be different, right? It depends on how we cut it. How many of you think it'll be the same? Almost everyone said it'll be the same no matter which cut you make, right? Yes? Do you see from our picture now that because it only makes sense to cut between 0 and 6, we're really just looking at that part of the graph? Kind of, but we don't have a vertex for a third degree polynomial. There's not a vertex formula. Well, there actually is, but it's more complicated than you would think. But in a calculus class, we would actually be able to find that point. But it's not negative b over 2a or anything like that. But what I'm trying to get at is from this picture, do you see now that you could maybe convince yourself that the cut does matter? Because look, this is saying that if you're really close to 0, your volume is going to be over here, and as you go out, the volume goes up, but it eventually has to come back down to 0. So the volume varies with the cut, right? And finding that highest point is not simple. Most people would look at this and say, oh, it's at 3, halfway, but that's not the case. It might be that this graph does this in reality. It might do this, something like that, and that point might be right there, and it's not quite in the center. Do you understand? So in a calculus class, you would have to have this to be able to answer the question. That's what you would have to work with. Do you all want to know what the answer is, or do you care? Are you curious? Okay, I'll do it. I'm going to do calculus though, and you don't need to ask. Don't ask me what what are you doing, or okay. Just let me do it. Okay. So what I'm going to do Take 12x squared minus 144x plus 288 equals 0. All right, I'm going to need a calculator. I have somehow put a quadratic equation up here, okay? And that comes from here. Don't worry about how it does. And then what I'm going to do from this is solve it. And this is a quadratic, right? So I'm going to use a quadratic formula. X is equal to negative b plus or minus the square root, and this is where I'll need my calculator. That's weird. I just reached in my pocket and the calculator screen was open. It's supposed to do that, I guess, right? So I'm going to square that, right? So I get 20,736 minus 4 times 12 times 288. Am I going to be subtracting this number or adding it? It'll be subtraction. 13,824 over 24. So 20,736 minus 13, 6,912. Take the square root of that. So I'm getting 144 plus or minus 83.14 divided by 24. I'm going to get two answers here. So 144 plus 83.14 divided by 24. So one of my answers is 9.46. The other answer, someone like put perfume on or something just now? No? Is that like lotion or something? Okay. The other one, 2.54. I'm rounding a little bit. Those are the answers. So do you remember the picture we just did? It went like this. It was 6 and 12 like that. And we said it went like up and then it came back down and then went back up like this. Okay. This highest point right here happens when your x value is 2.54. And the lowest point down here happens when your value is 9.46. But within the problem itself, this doesn't make sense. So between 0 and 6, it's 2.54 inches. So if I was going to do this and my business had to pay for this aluminum and I wanted to get the most volume out of that box, I would come cut 2.54 inches out of each corner, and then I would have a maximum volume possible. Now, yeah, great. So if I actually plugged in that point, and you're asking, so I'm going to answer. I don't want to leave anyone hanging here. So if I wanted to know what that maximum volume would be, I take that and I plug it in here. So I'll do that. 2.54 cubed, right? I'm doing that, times 4. So this would give me 65.55. Then minus, now I'm going to do the 2.54 squared times 72. Crap. This will be negative 464.51. And then 288 times 2.54, 731.52. So 731 subtract 464.51 plus 65.55 is 332.56. That's it. Someone gives you a sheet of aluminum that is 12 by 24 and you cut the corners out and fold them up, the most volume you're ever going to get, no one's ever going to do any better than this, is 332.56 cubic inches. That's the most you can get out of it. End of story. All right. Now, you can imagine that these optimization problems are used in business for real. I mean, you're shipping things and you want to get the most into a box because it costs money to put something up in an airplane and take it from point A to point B. You want to get everything you can in there, right? Unless you want your business to fail, then you can just go ahead and just go grab a box, man. All right, so wow, we only have 10 minutes. I kind of ate that whole last 30 minutes up. Sorry about that. Let's go ahead and let me put the problems that I want you to do at home. All right. So this will be turned in next time for a quiz, and I still have some work from you that I haven't given back and that I need to put in. I'll get caught up. Take home. Homework / quiz. First problem, sketch this. F of x equals negative x to the fourth plus 2x cubed plus, sorry, I have to make sure these work, 35x squared. Yep, that'll work. 2 f of x equals 5x to the sixth minus 125 x to the fourth. Three f of x equals, x squared plus 5x, oh, that was supposed to be cubed, sorry, cubed. 5x squared minus 4x minus 20. Okay, those are the three. And then let's do one problem, which will be a word problem. Let's do that same exact cardboard problem, okay? I'm just going to change, or aluminum problem. I'm just going to change the dimensions of the aluminum. Let's make it a 20-inch by 30-inch. And the instructions there are to come up with a formula, a volume function, and then to sketch it. Understand the directions on that? All right, let's have that ready tomorrow. Come up with a volume function. Remember, you're going to cut out the corners. So it's the same exact thing. Cut out the corners. And then you're going to come up with the volume function. And then I want you to sketch the volume function, which means you have to multiply everything together and expand it all out and get your leading coefficient and your degree.
So regardless of how big the corners are, we should always the same as what we cut out?
Well, because x is the cut, so we should all have the same function.
Okay.
Yeah. Yes?
Can we find the vertex anywhere?
Do what?
Vertex.
What vertex?
For 4.
Can you? Well, like I said, you have to do calculus to do that. Yeah. There's not a formula for it. Well, I mean, there is, but...
Well, I kind of figured out how you figured it out first.
You figure out how I did? Did you see the numbers, where the numbers came from?